Inverse functions and relations. So inverse relations exist if and only if one relation contains point BA whenever the other relation contains point AB, meaning you can switch the ordered pairs between the two functions, or you can switch the x and the y coordinate of the ordered pairs between the two functions. For example, let's take a look at this table. Our first point in table A is 1, 2. That would be an x value of 1 and a y value of 2. Whereas in the table, the second table, table B, we have a point 2, 1, where we have an x value of 2 and a y value of 1. You can see that the points are actually switched. Here we have an x value of 1, here we have a y value of 1. Y value of 2, x value of 2. So these are actually going to be switching locations. All right, this is called an inverse function. Switch your x and y coordinates, you end up with the inverse function. If we take a look at this graph right here, every point on this graph is going to have an inverse point. So we're going to start with the blue dot because that's the function f of x. That point right there is at 2, 1. It's actually the same point that I just talked about. The orange point is on the inverse function, and that point's at 1, 2. You can see that those points are switched x and y variables. Also, I get to this a little later in the notes, but function notation for the inverse function is when we use what looks like a little exponent of -1. So if we had the function f of x, the inverse of f of x would be written as f inverse of x, and it looks like, again, it looks like that exponent. The horizontal line test is much like the vertical line test, which we've previously done this year. The horizontal line test is when you run a horizontal line through the graph. A function has an inverse if and only if each horizontal line intersects the graph of the function in at most one point. For this first example set, the directions do say to graph the function using a graphing calculator, which we are not doing this year. So I'm just going to sketch what the graph would look like. Don't worry, like if you have any problems on homework or a quiz, you will be given the graph. You will not have to actually determine what the graph is. Anyways, number 1 is the graph of f of x is equal to the absolute value of x minus 1. So the graph of this function would look like this. Okay, and the directions are telling us to apply the horizontal line test to determine whether its inverse function exists. So a horizontal line can only intersect the graph in at most one location. This graph right here, it intersects twice. Therefore, the inverse function, which I'm going to label just as f of -1, which really stands for the inverse of f of x, does not exist. And number 2, if you were to type this function into your graphing calculator, you would get a graph that looks similar to this. I should do that in different colors so we can see it. All right, and if we were to draw a horizontal line across the graph at any point, it is only going to intersect this graph once. So because it only intersects the graph in one location on every horizontal line, we can say that the inverse function does exist. And that's all these questions are asking you for. You don't have to do anything else. You're just determining whether or not the function has an inverse. So in the On Your Own section, you don't even need a graphing calculator. The graphs are provided for you. Hopefully you recognize right away on number 1 that a horizontal line is going to intersect the graph multiple times. The inverse does not exist. Number 2 is just like the last one we did. At any location, if you draw a horizontal line, it's only going to intersect once. The inverse function does exist. One-to-one functions. So for each x value, there is exactly one y value, and for each y value, there is exactly one x value. Graphically, the function passes both the horizontal and the vertical line test. That's important right there. If you have a graph that passes both tests, then there is a one-to-one function. A quick note to add to this section is a note on domain and range. So if you know the domain of your f of x function, because you're switching the points like we talked about on the first page here, because you're switching your x and y points, and your x values are typically your input and your y values are typically your output or your range, that means the domain of f of x, which are the x values, is also the range of the inverse. Let me repeat what I said there. If you know that x values are inputs or domains and y values are outputs or the range, and you switch the ordered pairs to make an inverse function, that means you are also switching the domain and range. Domain of f of x becomes the range of the inverse, whereas the range of f of x becomes the domain of the inverse. Okay, this is going to be helpful because sometimes it's not as easy to find the domain and range, specifically the range, not as easy to find the range. So by knowing you can just interchange them, you should be able to find the values no matter what function you're dealing with, either the original or the inverse. Example set 2. We need to determine whether a function is one-to-one. The first example, we have a list of ordered pairs. When you have a list of ordered pairs, or if you're looking at a function on the graph, Remember that it needs to pass both the horizontal and vertical line test, which means there can be no repeated x values and also no repeated y values. You can only have 1 point on each of those horizontal or vertical lines. So always check or think to yourself, are there any repeated x or y coordinates? And if there are repeated x or y coordinates, then this is not a one-to-one function. If they are all unique, meaning they all are different, then yes, this would be a one-to-one function. For number 1, we have the domain or input values -2, 1, 0, 1, and 2. Right there, we have 2 repeated x values. So therefore, no, this is not one-to-one. Number 2, right here we can see that we have 2 x values or 2 inputs that are giving us the same output or y value, which also cannot happen. That is not one-to-one. Number 3 would pass every horizontal line test, and it would also pass every vertical line test. So therefore, yes, this is a function. All right, the directions also tell us to state the domain and range of the inverse function. So right here, we don't see the inverse function. We see the graph of the original function. But if we were to graph this as an inverse, meaning if we were to switch every one of these ordered pairs on this graph, we could easily do that and just visualize what we're looking at really quick. So I just marked 3 points on the graph. This point right here being at -1, 1. If I interchange -1, 1, I would be graphing a point at 1, -1, which is right here. 0, 0 is going to remain the same, and then we would end up graphing over that point as well. Now here's the only thing that's different. This graph is actually going to come down from up here, and it's going to go like that. That's the inverse. All right, so if we were to look at this, we could hopefully, well, I hope everyone could identify that the domain and range of the inverse function is going to be negative to positive infinity. For the first algebraic example, we have the function f of x is equal to x minus 1 divided by x plus 2. The first step in the above description tells us to switch f of x or replace f of x with y. That means we are only replacing this notation with the variable y. And it's still equal to our fraction of x minus 1 over x plus 2. The second step tells us to switch our x and y variables. Where I see that I have a y variable, I'm going to replace that with x. And where I see that I have a x variable, I'm going to replace that with y. The third step is to solve for y. So when you're solving for y and you have a fraction like this one, it does look a little bit complicated, and it is a few extra steps than what you're used to. But I will say that anytime you end up with a fraction like this, they all follow the same pattern. So if you follow with what I do right here, every time you end up with a fraction, it's a similar process. Obviously it has different numbers, but a very similar process. So for step 3, we're solving for y. In order to do that, we need to eliminate this fraction. We need to get rid of that. So in order to do that, I'm going to multiply both sides of my equation in step 2 by y plus 2. And the reason why I do that is because over here on the right side of the equal sign, that will eliminate my denominator. On the left side, I do have to distribute my value of x to both terms in the parentheses, giving me x times y plus 2x, and this is now equal to y minus 1. We want to solve for y, so let's isolate all y terms, or get all y terms to one side of the equal sign. To do that, I'm going to subtract xy from both sides. That gives me 2x is equal to y minus xy minus 1. And then I'm going to add 1 to both sides. I could have done that in the same step, but I'm writing out all my work. We end up with 2x plus 1 is equal to y minus xy. At this point, on the right side of the equal sign, both of my factors have a value of y. So I'm going to factor out a common factor of y. Two x plus 1 is equal to our common factor of y multiplied by 1 minus x. I'm still solving for y, so in order to isolate that value of y, I'm going to divide both sides by 1 minus x, and that is going to eliminate my value of 1 minus x on the right side. So at this point, I'm left with y equals 2x plus 1 over 1 minus x. And just note right there, I kind of switched the side of the equal sign that the y variable was on, but it's still the same expression as the step before. All right, the last step in the description above says to just replace y with the correct notation for f of x. So for step 4, I am going to replace where I see y with the notation the inverse of f of x is equal to, okay, there's no mathematical difference between these two steps right here other than the notation that I'm using. So the inverse of f of x is equal to 2x plus 1 divided by 1 minus x. And this here is your final answer. Like I said, fractions are going to be a little bit more involved. It's definitely a longer problem, but they do follow a similar process. So use this one as reference when you're completing other fraction problems, such as number 2 in the On Your Own section. All right, number 2, we have f of x is equal to the square root of x minus 4. Step 1, we're replacing f of x with y. We have y is equal to the square root of x minus 4. Step 2, replace your x and y variables or interchange your x and y variables. This becomes x equals the square root of y minus 4. I need to solve for y. Currently y is underneath the square root sign, so I need to get that out of the square root sign. The only way that we can eliminate the square root sign is to square both sides of our function. So this is step 3. When we square both sides of the function, we're left with x squared equals y minus 4. In step 3, we're solving for y, so add 4 to both sides. I have y equals x squared plus 4. That is my inverse function, but for the fourth and final step, I need to replace y with the correct function notation of the inverse of f of x is equal to x squared plus 4. The next set of examples is on graphing the inverse function. So graphing a one-to-one function is when you switch the x and y coordinates. You could make a table for this if you want, although you could probably do it right in your head. So let's start on the left side of the graph right here. This point is at -2, -1. If we were to switch these points, we would regraph this point at -1, -2. This point is located at -1, 0. If you switch the x and y coordinates, you would regraph that point at 0, -1. This last point is at 2, 1. Switch your x and y, you'd be at 1, 2. Connect to your points. And this orange graph is your inverse function. I'm just going to draw a dashed line that corresponds to the point we interchange the x and y variables from. That's not necessary, I just did that so you can see the points are the specific points we switched. All right, for number 2, our first ordered pair is at -4, -3. If we switch those points, we're going to graph -3, -4. We have a point at 3, -3, 1, and a new point at 1, -3. We have that point at -1, 3, and a new point at 3, -1. And the last point is at 2, 4, with its inverse point being at 4, 2. And for the last part of the notes, we're looking at compositions of inverse functions. So two functions are inverse functions if and only if you can prove that they both or both compositions are equal to x. The first one proving that f of g of x is equal to x, and the second one indicating that g of f of x is equal to x. So we would have to actually compute both of those to prove that we have inverse functions. For number 1, f of g of x is going to be, or f of x is equal to x cubed minus 8, and g of x is equal to the cube root of x plus 8. We're going to start by finding f of g of x. This is equal to f evaluated at the cube root of x plus 8. When we evaluate the function f at the cube root of x plus 8, we're substituting that in for our value of x, giving us the cube root of x plus 8 raised to the power of 3 minus 8. For for this expression, if you have a cube root and you cube it, when you simplify it, you're going to be left with just the expression of x plus 8, and then minus 8 for our last term here. X plus 8 minus 8 is the same thing as x, and that's exactly what we're looking for the first part. For the second part, we're going to prove that g of f of x is also equal to x. When we evaluate the function here, we have the g function being evaluated at x cubed minus 8. Substitute this into the function. We have the cube root of x cubed minus 8 plus 8. Minus 8 plus 8 is 0, leaving you with the cube root of x cubed. The cube root of a cubed number simplifies in this case to just x. Therefore, we just showed all our work to prove that g of f of x is equal to x. So therefore, we can say that f of x and g of x are inverse functions of each other. And for number 2, just follow along while I complete this problem.